How galaxies form. Theories, variance, and growth. Our best current theory about how galaxies form involves gravity, dark matter, and mergers. The universe contains billions of galaxies, of which our own Milky Way is just one. Often thought of as vast agglomerations of stars, which is how they look in photographs, galaxies actually contain other types of material as well, such as gas, dust, and dark matter. Astronomers know that galaxies began to form soon after the Big Bang, but they don't yet fully understand the process by which they ended up as we see them today. Here are some of the most promising theories of how galaxies form, how and why they merge, as well as the different varieties of galaxies that have been observed. As the universe expanded in size following the Big Bang, all the matter in it was spread out more and more thinly. At the same time, there was a competing effect, the force of gravity, that was pulling this generally diffuse matter into denser clumps. Some of the clumps were just transient affairs that eventually dissipated, but in other cases, the clump's gravity was strong enough to pull in more matter and allow it to grow. As the mass of the clump increased, so did its gravitational pull, causing it to collapse down to a smaller size and higher density. In this way, the first protogalaxies were able to form within the first few 100,000 years of the universe's existence, according to NASA's Goddard Space Flight Center. That much is pretty much agreed by all astronomers. What is less certain is how those first protogalaxies relate to the mature galaxies we see today. Essentially, there are two competing theories, called top-down and bottom-up. The top-down theory, dating from 1962, came first. According to this, the first clumps to collapse took the form of giant gas clouds which were comparable in total mass to present-day galaxies. As the gas collapsed and its density increased, some stars formed very early on, before the gas had stabilized into a rotating disk. These early stars formed the elliptical or bulge-like component of a galaxy, while later stars formed inside the much thinner disk component. The bottom-up theory, also known as the hierarchical clustering model, is more recent and generally considered a better match with current observational evidence. It introduces two new factors that didn't play a major role in the top-down model: dark matter and galactic mergers. We know that dark matter must exist in galaxies because of its effect on their rotation rates, and it seems likely that it played a key part in the original formation of galaxies. But the bottom-up theory, unlike the top-down theory, doesn't assume that the original protogalaxies must have been the same size as present-day ones. Instead, it takes the view that they were much smaller, and it was only later on that they grew to their present size through repeated mergers. Astronomers are pretty confident that mergers played some kind of role in shaping the galaxies we see today. One reason is that powerful telescopes like Hubble have revealed numerous examples of galactic mergers still occurring today. On top of that, the most distant galaxies, which, due to the finite speed at which light travels, are seen as they were billions of years ago, look distinctly smaller and less well-structured than nearby ones, according to NASA's JWST webpage. This seems a clear indication that galaxies must have evolved in the time between their original formation and today. Elliptical. Around a third of galaxies have very little gas or dust and no regions of active star formation. The largest of these, the giant ellipticals, can be up to 300,000 light-years across, while dwarf ellipticals measure only a few thousand light-years. Spiral. These are the most distinctive galaxies, consisting of a thin disk of gas, dust, and stars which displays an often spectacular-looking spiral pattern. Most spiral galaxies also have a small bulge at the center resembling an elliptical galaxy, and possibly a central bar. Irregular. This is the everything else category, neither a smooth, featureless ellipse nor a regular, symmetrical spiral. Irregular-looking galaxies become much more common at larger distances, in other words, earlier in the life of the universe. It's likely that, given time, they will merge into spirals or ellipticals. What is a spiral galaxy? Spiral galaxies are twisted collections of stars and gas that often have beautiful shapes and are made up of hot young stars. Most of the galaxies that scientists have discovered so far are spiral galaxies, as opposed to the other two main categories of galaxy shapes, elliptical and irregular. The Milky Way, the galaxy that includes Earth and our solar system, is an example of a spiral galaxy. Spiral galaxies make up roughly 72% of the galaxies that scientists have observed, according to a 2010 Hubble Space Telescope survey. Most spiral galaxies contain a central bulge surrounded by a flat, rotating disk of stars. The bulge in the center is made up of older, dimmer stars and is thought to contain a supermassive black hole. Approximately two-thirds of spiral galaxies also contain a bar structure through their center, as does the Milky Way. The disk of stars orbiting the bulge separates into arms that circle the galaxy. These spiral arms contain a wealth of gas and dust and younger stars that shine brightly before their quick demise. How the spiral arms form continues to puzzle scientists. One theory suggests the galaxy arms could be the result of density waves traveling through the outer disk. Encounters between galaxies could cause such waves as the mass of the smaller galaxy could affect the structure of the larger galaxy as the two combine. Spiral galaxies are thought to evolve into elliptical galaxies as the spirals get older, but it's unclear how common elliptical galaxies are as they're made up of older, dimmer stars and are more challenging to spot. One of the largest known spiral galaxies is NGC 6872, which is 522,000 light-years across from the tips of its outstretched spiral arms. That's about 5 times the size of the Milky Way. In 2017, astronomers discovered an 11-billion-year-old ancient spiral galaxy called A1689b11. Its discovery will help scientists understand how galaxies transition from highly chaotic, turbulent disks to more organized and thinner disks, like that of the Milky Way. What are elliptical galaxies? Elliptical galaxies are the most abundant type of galaxies found in the universe, but because of their age and dim qualities, they're frequently outshone by younger, brighter collections of stars. Elliptical galaxies lack the swirling arms of their more well-known siblings, spiral galaxies. Instead, they bear the rounded shape of an ellipse, a stretched-out circle. One of the most famous elliptical galaxies is Cygnus A, which is located roughly 600 million light-years from Earth and is an extremely bright radio source. Cygnus A is not only well known to astronomers, but has a place in science fiction. It was featured in the 1985 novel Contact, a Carl Sagan story that later inspired a Hollywood movie of the same name. In 1926, Edwin Hubble devised a system to classify galaxies. Known as the Hubble sequence, or the Hubble tuning fork, it organizes galaxies based on their shape. Under this organization, elliptical galaxies are classified by how stretched out they are. Galaxies classified as E0 appear to be almost perfect circles. Remember, a circle is an ellipse, while those listed as E7 seem much longer than they are wide. A galaxy's appearance is related to how it lies on the sky when viewed from Earth. A galaxy having the E7 shape but seen head-on would appear as an E0, for instance, because observers would not see its stretched shape, which lies behind it. Elliptical galaxies have a broader range in size than other types of galaxies. The smallest are dwarf elliptical galaxies, which can be less than 10% of the size of the Milky Way. But ellipticals can also stretch to more than 1 million light-years across and contain more than 10 trillion stars. M87, identified as one of the largest galaxies in the universe, is classified as an E0 elliptical galaxy. Astronomers have identified more spiral galaxies than ellipticals, but that's simply because the spirals are easier to spot. While spiral galaxies are bright, elliptical galaxies are dim. Spiral galaxies are hotbeds of star formation, but elliptical galaxies aren't nearly as prolific because they contain less gas and dust, which means fewer new and brighter stars are born. The existing stars inside an elliptical galaxy tend to be older, giving off more red light than younger stars. So, why do astronomers think elliptical galaxies dominate the sky? Because when specific regions of the sky are studied in depth, more elliptical galaxies appear. Astronomers think such counts are consistent throughout the universe. Because elliptical galaxies contain older stars and less gas, scientists think that they are nearing the end of the evolutionary line for galaxies. The universe is a violent place, and collisions between galaxies are frequent. Indeed, the Milky Way is due to crash into the Andromeda Galaxy in a few billion years. When two spirals collide, they lose their familiar shape, morphing into the less structured elliptical galaxies. A supermassive black hole is thought to lie at the center of these ancient galaxies. These gluttonous giants consume gas and dust and may play a role in the slower growth of elliptical galaxies. Born from collision, elliptical galaxies are more commonly found around clusters and groups of galaxies. They are less frequently spotted in the early universe, which supports the idea that they evolved from the collisions that came later in the life of a galaxy. Research in just the past few years has revealed quite a bit about the evolution of elliptical galaxies. A 2014 study showed that supermassive black holes might be stopping star formation in elliptical galaxies, which would help explain why there are so few new stars in ellipticals. Previously, astronomers thought ellipticals lacked the cold gas necessary for star formation, but the new study showed that there is actually a lot of cold gas in ellipticals. It's just blasted away by supermassive black holes in the region. In 2015, researchers discovered that some compact ellipticals might lose most of their mass through galaxy interactions, which has large implications for what happens when galaxies merge and collide. Galaxy mergers with ellipticals could even produce weird hybrids, such as the Sombrero Galaxy. A 2012 examination by NASA's Spitzer Space Telescope found that Sombrero is made up of one galaxy inside of another. The study reclassified Sombrero to an elliptical galaxy with a flat disk inside of it. Such examinations sometimes also reclassify elliptical galaxies into other types, such as with UGC 1382 in 2016. Scientists determined that the galaxy was not an elliptical, but a sort of strange combination of cosmic pieces that came about through various mergers. Scientists are now interested in how many other similar galaxies reside in our universe. Join our The Curiosity Dude channel to keep talking space on the latest missions, night sky, and more. And if you have a news tip, correction, or comment, let us know. Please don't forget to subscribe to our channel, like this video, and share video with your friends.
What is dark energy? Inside our accelerating, expanding universe. Some 13.8 billion years ago, the universe began with a rapid expansion we call the Big Bang. After this initial expansion, which lasted a fraction of a second, gravity started to slow the universe down. But the cosmos wouldn't stay this way. 9 billion years after the universe began, its expansion started to speed up, driven by an unknown force that scientists have named dark energy. But what exactly is dark energy? The short answer is, we don't know. But we do know that it exists. It's making the universe expand at an accelerating rate. And approximately 68.3 to 70% of the universe is dark energy. Dark energy wasn't discovered until the late 1990s, but its origin in scientific study stretches all the way back to 1912 when American astronomer Henrietta Swan Leavitt made an important discovery using Cepheid variables, a class of stars whose brightness fluctuates with a regularity that depends on the star's brightness. All Cepheid stars with a certain period. A Cepheid's period is the time it takes to go from bright to dim and bright again, have the same absolute magnitude or luminosity, the amount of light they put out. Leavitt measured these stars and proved that there is a relationship between their regular period of brightness and luminosity. Leavitt's findings made it possible for astronomers to use a star's period and luminosity to measure the distances between us and Cepheid stars in far-off galaxies, and our own Milky Way. Around this same time in history, astronomer Vesto Slipher observed spiral galaxies using his telescope spectrograph, a device that splits light into the colors that make it up, much like the way a prism splits light into a rainbow. He used the spectrograph, a relatively recent invention at the time, to see the different wavelengths of light coming from the galaxies in different spectral lines. With his observations, Slipher was the first astronomer to observe how quickly the galaxy was moving away from us, called redshift, in distant galaxies. These observations would prove to be critical for many future scientific breakthroughs, including the discovery of dark energy. Redshift is a term used when astronomical objects are moving away from us and the light coming from those objects stretches out. Light behaves like a wave, and red light has the longest wavelength. So, the light coming from objects moving away from us has a longer wavelength, stretching to the red end of the electromagnetic. Discovering an expanding universe. The discovery of galactic redshift, the period luminosity relation of Cepheid variables, and a newfound ability to gauge a star or galaxy's distance eventually played a role in astronomers observing that galaxies were getting farther away from us over time, which showed how the universe was expanding. In the years that followed, different scientists around the world started to put the pieces of an expanding universe together. In 1922, Russian scientist and mathematician Alexander Friedmann published a paper detailing multiple possibilities for the history of the universe. The paper, which was based on Albert Einstein's theory of general relativity published in 1917, included the possibility that the universe is expanding. In 1927, Belgian astronomer Georges Lemaître, who is said to have been unaware of Friedmann's work, published a paper also factoring in Einstein's theory of general relativity. And, while Einstein stated in his theory that the universe was static, Lemaître showed how the equations in Einstein's theory actually support the idea that the universe is not static, but, in fact, is actually expanding. Astronomer Edwin Hubble confirmed that the universe was expanding in 1929 using observations made by his associate, astronomer Milton Humason. Humason measured the redshift of spiral galaxies. Hubble and Humason then studied Cepheid stars in those galaxies, using the stars to determine the distance of their galaxies, or nebulae, as they called them. They compared the distances of these galaxies to their redshift and tracked how the farther away an object is, the bigger its redshift and the faster it is moving away from us. The pair found that objects like galaxies are moving away from Earth faster the farther away they are, at upwards of hundreds of thousands of miles per second, an observation now known as Hubble's law, or the Hubble-Lemaître law. The universe, they confirmed, is really expanding. Expansion is speeding up, supernovae show. Scientists previously thought that the universe's expansion would likely be slowed down by gravity over time, an expectation backed by Einstein's theory of general relativity. But in 1998, everything changed when two different teams of astronomers observing far-off supernovae noticed that, at a certain redshift, the stellar explosions were dimmer than expected. These groups were led by astronomers Adam Rees, Saul Perlmutter, and Brian Schmidt. This trio won the 2011 Nobel Prize in Physics for this work. While dim supernovae might not seem like a major find, these astronomers were looking at Type 1a supernovae, which are known to have a certain level of luminosity. So they knew that there must be another factor making these objects appear dimmer. Scientists can determine distance and speed, using an object's brightness, and dimmer objects are typically farther away, though surrounding dust and other factors can cause an object to dim. This led the scientists to conclude that these supernovae were just much farther away than they expected by looking at their redshifts. Using the object's brightness, the researchers determined the distance of these supernovae, and using the spectrum, they were able to figure out the object's redshift and, therefore, how fast they were moving away from us. They found that the supernovae were not as close as expected, meaning they had traveled farther away from us faster than anticipated. These observations led scientists to ultimately conclude that the universe itself must be expanding faster over time. While other possible explanations for these observations have been explored, astronomers studying even more distant supernovae or other cosmic phenomena in more recent years continued to gather evidence and build support for the idea that the universe is expanding faster over time, a phenomenon now called cosmic acceleration. But, as scientists built up a case for cosmic acceleration, they also asked, why? What could be driving the universe to stretch out faster over time? Enter dark energy. What exactly is dark energy? Right now, dark energy is just the name that astronomers gave to the mysterious something that is causing the universe to expand at an accelerated rate. Dark energy has been described by some as having the effect of a negative pressure that is pushing space outward. However, we don't know if dark energy has the effect of any type of force at all. There are many ideas floating around about what dark energy could possibly be. Here are 4 leading explanations for dark energy. Keep in mind that it's possible it's something else entirely. Vacuum energy. Some scientists think that dark energy is a fundamental, ever-present background energy in space known as vacuum energy, which could be equal to the cosmological constant, a mathematical term in the equations of Einstein's theory of general relativity. Originally, the constant existed to counterbalance gravity, resulting in a static universe. But when Hubble confirmed that the universe was actually expanding, Einstein removed the constant, calling it "my biggest blunder," according to physicist George Gamow. But when it was later discovered that the universe's expansion was actually accelerating, some scientists suggested that there might actually be a non-zero value to the previously discredited cosmological constant. They suggested that this additional force would be necessary to accelerate the expansion of the universe. This theorized that this mystery component could be attributed to something called vacuum energy, which is a theoretical background energy permeating all of space. Space is never exactly empty. According to quantum field theory, there are virtual particles, or pairs of particles and antiparticles. It's thought that these virtual particles cancel each other out almost as soon as they crop up in the universe, and that this act of popping in and out of existence could be made possible by vacuum energy that fills the cosmos and pushes space outward. While this theory has been a popular topic of discussion, scientists investigating this option have calculated how much vacuum energy there should theoretically be in space. They showed that there should either be so much vacuum energy that, at the very beginning, the universe would have expanded outwards so quickly and with so much force that no stars or galaxies could have formed, or there should be absolutely none. This means that the amount of vacuum energy in the cosmos must be much smaller than it is in these predictions. However, this discrepancy has yet to be solved and has even earned the moniker the cosmological constant problem. Quintessence. Some scientists think that dark energy could be a type of energy fluid or field that fills space, behaves in an opposite way to normal matter, and can vary in its amount and distribution throughout both time and space. This hypothesized version of dark energy has been nicknamed quintessence after the theoretical fifth element discussed by ancient Greek philosophers. It's even been suggested by some scientists that quintessence could be some combination of dark energy and dark matter, though the two are currently considered completely separate from one another. While the two are both major mysteries to scientists, dark matter is thought to make up about 85% of all matter in the universe. Space wrinkles. Some scientists think that dark energy could be a sort of defect in the fabric of the universe itself. Defects like cosmic strings, which are hypothetical one-dimensional wrinkles thought to have formed in the early universe. A flaw in general relativity. Some scientists think that dark energy isn't something physical that we can discover. Rather, they think there could be an issue with general relativity and Einstein's theory of gravity and how it works on the scale of the observable universe. Within this explanation, scientists think that it's possible to modify our understanding of gravity in a way that explains observations of the universe made without the need for dark energy. Einstein actually proposed such an idea in 1919 called unimodular gravity, a modified version of general relativity that scientists today think wouldn't require dark energy to make sense of the universe. The future. Dark energy is one of the great mysteries of the universe. For decades, scientists have theorized about our expanding universe. Now, for the first time ever, we have tools powerful enough to put these theories to the test and really investigate the big question. What is dark energy? NASA plays a critical role in the ESA, European Space Agency, mission Euclid, launched in 2023, which will make a 3D map of the universe to see how matter has been pulled apart by dark energy over time. This map will include observations of billions of galaxies found up to 10 billion light-years from Earth. NASA's Nancy Grace Roman Space Telescope, set to launch by May 2027, is designed to investigate dark energy, among many other science topics, and will also create a 3D dark matter map. Roman's resolution will be as sharp as NASA's Hubble Space Telescopes, but with a field of view 100 times larger, allowing it to capture more expansive images of the universe. This will allow scientists to map how matter is structured and spread across the universe and explore how dark energy behaves and has changed over time. Roman will also conduct an additional survey to detect Type Ia supernovae. In addition to NASA's missions and efforts, the Vera C. Rubin Observatory, supported by a large collaboration that includes the U.S. National Science Foundation, which is currently under construction in Chile, is also poised to support our growing understanding of dark energy. The ground-based observatory is expected to be operational in 2025. The combined efforts of Euclid, Roman, and Rubin will usher in a new golden age of cosmology, in which scientists will collect more detailed information than ever about the great mysteries of dark energy. Additionally, NASA's James Webb Space Telescope, launched in 2021, the world's most powerful and largest space telescope, aims to make contributions to several areas of research and will contribute to studies of dark energy. NASA's SPHEREx, the spectrophotometer for the history of the universe, epoch of reionization, and ICE's Explorer mission, scheduled to launch no later than April 2025, aims to investigate the origins of the universe. Scientists expect that the data collected with SPHEREx, which will survey the entire sky in near-infrared light, including over 450 million galaxies, could help to further our understanding of dark energy. Friends, I hope that you enjoyed this video and learned something new. I thank NASA for the work it does to explore space. I also hope that you did not forget to like this video and subscribe to this channel so as not to miss the interesting information that we regularly release for you. Please write in the comments what you would like to hear about next time. See you in the next video. Hello friends, and welcome to the channel The Curiosity Dude. Today, we will again plunge into the wonderful world of space and knowledge. We will count how many stars die in our Milky Way galaxy and find out whether a star can become a planet. We will also learn a few more amazing things about our universe that will not leave you indifferent. However, before we plunge into this wonderful world of space, hypotheses, and knowledge, I ask you to support this channel with your subscription and this video with your like. And don't forget to share the link to this video with your friends. It's a great idea. Now let's count together how many stars there are in our Milky Way galaxy. How many stars in the Milky Way die each year? When you gaze up at the stars, you see the same constellations that the ancient Greeks and even the early hunter-gatherers did. But it's also a changing tapestry, as new stars are constantly being born and others are dying. In fact, that will be the fate of our own sun in roughly 5 billion years. But how quickly does the night sky change, and in our galaxy, the Milky Way, how many stars die each year? According to James de Buizer, a research scientist at the Search for Extraterrestrial Intelligence, SETI, Institute, it's complicated. First, it helps to clarify what it means for a star to die. Stars are enormous balls of hot gas sustained by nuclear fusion that converts hydrogen to helium inside the core. Stars die when nuclear fusion stops. There are two main ways this can happen, and the way a star dies depends on its mass. For low-mass stars, nuclear fusion ends when all the hydrogen in the star's core is converted to helium. Without the heat and subsequent outward pressure of fusion, the star collapses onto itself. During this collapse, the pressure on the core becomes so intense that the remaining helium starts to fuse into carbon and release energy, NASA explains. The star's outer atmosphere puffs out and turns reddish to create what's known as a red giant. Eventually, the star sheds this puffy atmosphere, leaving behind a dense object known as a white dwarf. About 97% of the stars in the Milky Way, including the Sun, are destined to become white dwarfs, de Buizer said. Astronomers can see white dwarfs because they emit a unique light signature. They use this information, plus the rate of star formation and the total number of stars, to figure out how many stars die each year. It's estimated that one white dwarf forms every 2 years, de Buizer said. For stars that are 8 or more times the mass of the Sun, there's a different death process. These massive stars make up only about 3% of the Milky Way stars, but their impacts are impressive. These are the really violent, energetic events that I think some people might characterize as death, said Eric Borowski, an astrophysics graduate student at Louisiana State University. This kind of star fuses heavier and heavier elements in its core, eventually becoming so massive that it cannot hold itself up against gravity, Borowski said. The result is a huge explosion called a supernova. The star's core lives on as either a neutron star or a black hole, according to NASA. The last recorded observation of a supernova in the Milky Way was in 1604, yet astronomers estimate that a supernova happens once or twice a century in the galaxy. So why has it been more than 400 years since one has been detected in our galaxy? Astronomers' best estimates are complicated by the Milky Way shape and the dense clouds of gas and dust. There could be supernovae going off on the other side of the galactic center, but there's so much stuff between us, we're not going to see them, de Buizer said. In total, with the white dwarf forming every 2 years or so, plus a couple of supernovas happening every 100 years, that's a grand total of nearly 53 stars dying each century in the Milky Way, or about 1 star every 1.9 years. Understanding the stages of star death is how astronomers piece together star life cycles, de Buizer said. Could a star ever become a planet? Most scientists say a star can never become a planet, but the boundaries between these stellar objects can sometimes be murky. Stars twinkle in the night sky, even millions of light years away, because they are incredibly hot. Planets are much cooler. In between, brown dwarfs are an astronomical enigma. More massive than planets, but smaller than stars, they fit neatly into neither category. Sometimes, astronomers call these objects failed stars. But if you fail as a star, can you succeed as a planet? In other words, can a star or a brown dwarf become a planet? It's an intriguing idea, but for many astronomers, the answer is no. Stars and planets, just based on the way that they form, are two different things, said Covey Rose, a doctoral candidate of astronomy at the University of Sydney in Australia. Stars, and likely brown dwarfs, form when clouds of gas clump together through gravity. Thanks to their large mass, Rose said, stars sustain nuclear fusion, turning hydrogen into heavier elements. First helium, then carbon, then iron. Brown dwarfs don't get massive enough to fuse ordinary hydrogen, but they can briefly fuse a heavier version of it known as deuterium, according to the International Astronomical Union. Like planets, brown dwarfs cool as they age. Many stars, however, explode when they die, spreading a bunch of other material around the universe, Rose said. New stars form from the leftover gas. As they do, heavier elements swirl around them in disks. That leftover material will form rocky pebbles and planetesimals, and then eventually planets, Rose said. Stars and brown dwarfs form from gas, whereas planets form from heavier elements. By definition, then, a star can never turn into a planet. Still, definitions evolve. For much of history, stars and planets were defined by their patterns of movement in the sky. Eventually, people learned that planets circled stars. Now, astronomers know that stars and brown dwarfs can also circle each other, and that some planets circle nothing. Brown dwarfs, which were only hypothesized in the 1960s and observed in the 1990s, complicate traditional definitions further. They are neither failed stars nor souped-up planets, but kind of their own thing, said Evgenia Shkolnik, a professor of astrophysics at Arizona State University. Rose agreed, but even a third category doesn't quite capture the nuances of these celestial objects. The better we get at understanding things, the more we understand that things exist on a spectrum, Rose said. Often, stars, brown dwarfs, and planets are defined by size. Stars are at least 80 times the size of Jupiter, the approximate mass required for hydrogen fusion, Rose said, while brown dwarfs are 12 to 80 times the size of Jupiter, the approximate mass required for deuterium fusion. But many celestial bodies complicate these categories. Some planets, like the gas giant Jupiter, can get big enough to gravitationally accrete gas on top of their rocky cores, and some of these gassy planets are big enough to fuse deuterium. Brown dwarfs, meanwhile, lose the ability to fuse deuterium over time. On the other end of the spectrum, Rose recently identified the coolest brown dwarf known to emit radio waves, a property more often associated with stars. Because of these overlaps, many astronomers prefer to define these objects based on their origins, not on their masses. As long as these celestial bodies are defined by how they were formed, brown dwarfs will never become planets, but stay tuned. I think you could in some ways draw a comparison to the debate over Pluto's status as a planet, Rose said. Pluto was demoted to a dwarf planet in 2006 because the International Astronomical Union changed its definitions. In the future, some brown dwarfs could be likewise reclassified as planets. And while one star will never become one planet, it could become part of many, for the same reason people say, we are all made of stardust. When a star explodes, that star will eventually be recycled into the next generation of planets and everything else, Shkolnik said. I think it's lovely. Does every star have planets? Are some stars solo, or do they all have planetary families? In 1992, astronomers discovered the first planet outside the solar system. Since then, telescopes have spotted thousands of these so-called exoplanets orbiting not only stars similar to the Sun, but also in binary star systems, small, cool stars called red dwarfs, and even ultra-dense neutron stars. It's enough to make you wonder, does every star out there have at least one planet orbiting it? In a word, no, said Jonathan Lunine, chair of the Department of Astronomy at Cornell University. That is, at least not as far as we know. It's always a question of whether you can detect something or not, Lunine told Live Science. One doesn't know for sure, but it's certainly the case that there are plenty of stars where there have been searches for planets, and none have been found to date. Scientists estimate that there are as many planets as stars in our galaxy, Lunine said. but those planets aren't evenly distributed. Some stars, like the Sun, as well as TRAPPIST-1, a red dwarf star about 40 light-years away, are home to more than half a dozen planets, while others may have none. But what makes one star host so many planets while others fly solo? Scientists think it stems from the way the star formed. When young stars are forming, they're usually surrounded by a ring of dust particles. These particles crash into each other to form larger and larger clumps, which can eventually form planets. But not all young stars are so lucky. If you have a star which is formed from a clump of interstellar cloud that happens to have a very rapid rotation, as that clump is contracting instead of spinning out to form a disk, it might break into two or even more pieces and form a binary star system or multiple star system, Lu9 said. And in those cases, if a disk hasn't formed, it's possible that the system of 2 stars or 3 stars never ends up with a planet. Binary star systems can form planets in some cases, as in the case of Kepler-47 and its 3 planets, but the conditions have to be just right. There are binary star systems where there are planets, Lu9 said. So do those systems end up with the material breaking into 2 clumps and then a disk forming around one of those clumps, or maybe both of those clumps? Was there perhaps something that was captured? More rarely, a young star's dust-filled clump might spin so slowly that it simply collapses into a star without ever forming a disk, Lu9 said. It's also possible for a star to form planets only for the intense gravity of another star to slingshot them out of the solar system, or at least send them too far out to be detected. That may have been what happened to the planet HD 106906b, which circles a binary star system at an off-kilter orbit 18 times farther from its star than Pluto is from the Sun. But Lu9 warned that our knowledge of how many stars host planets is subject to what we can detect. That's because many planets are detected using the transit method, which uses dips in a star's brightness as a telltale sign that a planet is passing in front of it. We can always look at a particular star and say, well, a planet wasn't detected around it, but maybe there's a planet that's kind of small and really orbiting far from the star and doesn't transit the star and therefore is kind of stealthy. That's always a possibility, but more than likely, there are stars that really don't have planets around them. Friends, I hope you enjoyed this video and learned a lot of new things. On this channel, we try to keep you up to date with all the latest space exploration. We hope for your support. We hope for your subscriptions and your likes. Please write in the comments whether this video was interesting and useful for you. What else would you like to know? The solar system. Facts about our cosmic neighborhood. The solar system is a collection of planets, moons, asteroids, comets, dust, the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. Between Mars and Jupiter is a collection of asteroids known as the Others have been traveling around the solar system since its beginning, before the planets even existed. The Allende meteorite, which fell to Earth in 1969 and scattered over Mexico, is the oldest known meteorite, at 4.55 billion years old. How did our solar system form? Scientists think the solar system formed when a nearby exploding star, called a supernova, triggered the collapse of the solar nebula. According to this theory, the explosion sent shock waves through space, and those shock waves pushed parts of the nebula closer together, leading to collapse. The supernova may have even seeded material into the nebula, Live Science previously reported. For instance, scientists have found that aluminum-26, an element formed only in the hearts of stars, most likely originated from a series of nearby supernovas, Live Science sister site-based com reported. The Sun. The Sun is at the center of the solar system and is its largest object, accounting for approximately 99.8% of the solar system's mass, according to the University of California, San Diego. The Sun is a giant, raging ball of fire powered by nuclear reactions, and it provides the energy that sustains life on Earth. The yellow dwarf star is made up of gas, about 91% hydrogen and 8.9% helium, according to NASA. Compared with other stars, the Sun is relatively small and just one of hundreds of billions of stars in our home galaxy, the Milky Way. The Sun is about 26,000 light-years from the center of our galaxy. According to NASA, the Milky Way is a spiral galaxy with curved arms of stars emanating from its center. The solar system is located in one of the smaller arms, called the Orion Cygnus Arm, or simply the Orion Arm. The Milky Way is huge compared with the solar system. If the solar system were the size of your hand, the Milky Way would be as big as North America, according to NASA Jet Propulsion Laboratory's Night Sky Network. Our solar system's planets. 8 confirmed planets and many dwarf planets orbit the Sun. According to NASA, the order and arrangement of the planets and other bodies in our solar system is due to the way the solar system formed. Rocky materials could withstand the young sun's immense heat, so the first 4 planets, Mercury, Venus, Earth, and Mars, are small, with rocky surfaces. Beyond them, materials we are used to seeing as ice, liquid, or gas settled in the outer regions of the young solar system. NASA says, namely the gas giants Jupiter and Saturn and the ice giants Uranus and Neptune. Mercury. Mercury is the closest planet to the Sun. It is also the smallest planet in the solar system. At about 3,032 miles, 4,879 kilometers in diameter, it is only slightly larger than Earth's moon and has no moons of its own. Mercury has no atmosphere to protect it from the Sun's relentless radiation, and surface temperatures can reach highs of 800 degrees Fahrenheit, 427 degrees Celsius, during the day and plummet as low as -290 F, -179 C, at night. Because of its speedy rotation around the Sun, Mercury was named after the Roman messenger of the gods, Venus. Named after the Roman goddess of love, Venus is the second planet from the Sun and the hottest planet in the solar system. Its atmosphere is a thick layer of mostly carbon dioxide gas that traps heat, allowing the planet's surface temperatures to reach a scorching 880 F, 471 C. At 7,520 miles, 12,100 kilometers in diameter. According to NASA, Venus is slightly smaller than Earth and, like our planet, has a core of molten iron. In 2020, astronomers announced that they discovered phosphine in the atmosphere of Venus. On our planet, this chemical is almost always made by living creatures, leading some researchers to wonder if Venus clouds might host life. However, the findings are controversial and have yet to be fully confirmed. Indeed, other work has suggested that it would be too difficult for any creatures to survive in such a hellish place because of the lack of much liquid water. Earth. The third rock from the Sun, Earth is the only planet in the universe known to harbor life. Its habitability is linked to the presence of liquid water. Earth is located in the so-called Goldilocks zone, meaning it orbits at the ideal distance from the Sun to have liquid water. If it were any closer, the water would evaporate into a gas, and if Earth were farther away, the water would freeze. About 71% of our planet's surface is covered in water, according to the U.S. Geological Survey, and Earth's atmosphere protects the planet from solar radiation. Earth is the only planet not named after a god. Earth likely earned its name from the English and German words for ground. The blue planet is the largest of the 4 rocky planets in the solar system, and it has 1 moon. Scientists think Earth's moon was formed from a piece of Earth that broke off when a giant object smashed into the young planet.
Mars.
Mars is known as the red planet because of the iron-rich dust that covers its surface and gives it a rusty color. This red hue led the ancient Romans to name Mars after their god of war. Mars, the fourth planet from the Sun, is home to the largest volcano in the solar system, Olympus Mons. The planet has a thin atmosphere, and without a thick protective shield, temperatures on Mars average around -80 F, -60 C. It is likely that liquid water, which would provide a home for life as we know it, existed on the Martian surface billions of years ago. And some scientists think Mars may still have liquid water on its surface today. Mars has two moons, Phobos, which may have formed from ancient rings around the planet, and Deimos, which may have been knocked into its current orbit by an ancient, no longer existing moon. Jupiter. Jupiter is the biggest planet in the solar system. Unlike the inner planets, Jupiter is a gas giant, made up mainly of helium and hydrogen. It is named after the king of the Roman gods, also known as Zeus in the Greek pantheon. Jupiter, the fifth planet from the Sun, is twice as big as all of the other planets in the solar system combined. Yet it also has the shortest day of any planet, taking 10 hours to turn about its axis, according to NASA. Jupiter is surrounded by dozens of moons, and its rings are faint and composed of dust. Deep in the planet's atmosphere, high pressure and high temperatures have compressed the hydrogen gas into a liquid, creating the largest ocean in the solar system, according to NASA. Saturn. Saturn, the sixth planet from the Sun, is the second largest planet in the solar system. Saturn is best known for its prominent rings. Like Jupiter, Saturn is a gas giant composed of helium and hydrogen, and it is the least dense of the planets. Saturn's rings are made of billions of ice particles and rocks. The ringed planet also has dozens of moons, ranging in size from that of a sports field to the size of Mercury, according to NASA. One of Saturn's moons, Enceladus, is covered in an icy ocean that astronomers say makes this moon a promising candidate for extraterrestrial life. Uranus. Uranus, the seventh planet from the Sun, was the first planet to be discovered using a telescope by British astronomer William Herschel in 1781. The ice giant is composed of heavier elements than its gas giant neighbors, a mixture of water, methane, and ammonia ice. Unlike other planets in the solar system, Uranus effectively orbits on its side, with its axis almost pointing toward the Sun, and it rolls like a ball as it travels around the Sun. Methane gas in Uranus' atmosphere makes the planet appear green-blue. The planet has 13 rings and 27 moons. It is the only planet to be named after a Greek deity, Uranus the sky god, rather than a Roman one. Neptune. Neptune, the eighth planet from the Sun, was discovered in 1846. However, even before observing the planet for the first time, scientists predicted its existence because of its effect on Uranus' orbit. Neptune, which is named after the Roman sea god, is so far from the Sun that it takes 4.15 hours for sunlight to reach the planet, according to Cornell University. For comparison, it takes about 8 minutes for sunlight to reach Earth. When the light arrives at Neptune, it is 900 times dimmer than what we see on Earth, according to NASA. Neptune is made up of water, methane, and ammonia surrounding a small, rocky core. Strong winds on the planet propel clouds of frozen methane at speeds of up to 1,200 miles per hour, 2,000 kilometers per hour. Neptune has 14 known moons, one of which was rediscovered after going missing for 20 years. Why is Pluto not a planet? Pluto, once considered the ninth planet in the solar system, was reclassified as a dwarf planet in 2006 because it failed to meet one of the criteria in the definition of a planet. The International Astronomical Union defines a planet as a celestial body that orbits the Sun, has enough gravity to pull itself into a round or almost round shape, and has cleared the neighborhood around its orbit. Pluto has not cleared the neighborhood around its orbit, so it's not considered a planet. Some astronomers believe this reclassification is unfair and that Pluto should be reinstated as the 9th planet in the solar system. Looking at the historical literature, Philip Metzger, a planetary scientist at the University of Central Florida, found that before the 2006 decision, the clearing the neighborhood rule appeared only in a single 1801 paper. He and his colleagues concluded that this Pluto excluding rule is arbitrary and not based on historical precedent, Live Science previously reported, and that therefore Pluto should still be considered a planet. Pluto, which is named after the Roman god of the underworld, sits in the vast Kuiper Belt, a region beyond Neptune that contains trillions of icy objects. There is a possible candidate to fill Pluto's vacancy as the 9th planet, Planet X or Planet 9. In a 2016 paper published in the Astronomical Journal, California Institute of Technology astronomers Mike Brown and Konstantin Batygin hypothesized that a planet 10 times larger than Earth could be orbiting the Sun about 20 times farther away than Neptune does. All those people who are mad that Pluto is no longer a planet can be thrilled to know that there is a real planet out there still to be found, Brown said at the time. Now, we can go and find this planet and make the solar system have 9 planets once again. However, Planet 9's existence is still theoretical because the planet has not been directly observed, according to NASA. Between the planets, between Mars and Jupiter, there is a huge collection of asteroids known as the main asteroid belt. These space rocks are leftovers from the formation of the solar system, and there are over 1 million known asteroids all over the solar system, according to NASA. Asteroids come in a wide variety of types and are classified based on their composition. Beyond the planets, beyond the ice giant Neptune, the solar system extends to the Kuiper Belt and the Oort cloud. The Kuiper Belt, whose existence was confirmed in 1992, is 30 to 55 astronomical units AU wide, according to NASA. 1 AU is the average distance between Earth and the Sun, about 93 million miles, or 150 million kilometers. The Kuiper Belt's most famous inhabitant is Pluto, but the region also contains hundreds of thousands of frozen objects 62 miles, 100 kilometers, or larger in diameter, many of which are remnants of the early solar system, according to NASA. The Oort cloud, which is a collection of comets different than the Kuiper Belt because it is located far, far in the solar system's icy outer reaches, has been hypothesized since the 1950s, but it has never been observed. Friends, today we learned a lot of interesting things about our solar system. I hope you enjoyed the video and learned something new. I also hope for your support for this video. Please don't forget to like it. And don't forget to subscribe to the channel so you don't miss interesting videos about space. We'll see you in the next interesting video.